Okay, so let us start today's session. So, do you remember last class what we have covered? Yes, you remember last class what we have covered? We have discussed about AC circuits, means we are just going to start. So, we discussed about what? We discussed about RMS voltage, we discussed about peak voltage, average voltage, how to calculate all that. Correct. So today we will go into AC circuits. I think in AC circuit purely resistive we have to. Did we cover purely resistive circuit in the last class? Tell me. Yes, Sam. Did we cover purely resistive circuit? Purely resistive circuit. Huh? Did we cover that? We have covered it. Inductive also completed. Capacitive not done, right? Let us start purely capacitive circuit. Yes, purely capacitive circuit. Okay, so there is a capacitor, capacitance C, and it is connected with a AC source. This V is equal to V naught sine omega t. Okay, so we know that if you take Q, Q is equal to C into V, you can write. So I is equal to dq by dt, we can write. Okay, and this is C into V, differentiation with time. So C comes out dv by dt, and V is nothing but V naught sine omega t. Right, differentiate this with respect to time. So V naught comes out, sine differentiation become cos, and omega also comes out. So from here, this I is equal to omega c V naught cos omega t. I think we have covered, isn't it? I think so. We have done this. Okay. Anyway, let me just try. So let us summarize them. I think we have completed the fundamental AC circuits. Now this fundamental AC circuit, briefly let us review that. Then only we will go to LCR circuit. Okay, series LCR circuit. So we have discussed resistive, purely resistive. We have discussed purely inductive, then purely capacitive. Capacitive. So in purely resistive, what happens? There is a resistor R, it is connected with AC source. V equal to V naught sine omega t. Similarly, if purely inductive, there is an inductor R connected with AC signal. V equal to V naught sine omega t. There is a capacitor C connected with AC voltage V equal to V naught sine omega t. So we have solved out equation of for current. If you remember, current I is equal to I naught, or capital I if you want, you write it whatever it is. So capital I is equal to I naught sine omega t. So here I naught is going to be V naught by R e. Okay, and here similarly current I is equal to minus I naught cos omega t, which can also be written as I naught sine omega t minus 90 degree or pi by 2. Okay, and here I naught is equal to V naught by XL. XL is equal to omega L, inductive reactance. Similarly, here also I is equal to I naught cos omega t. Here I naught is equal to V naught by XC. XC is equal to 1 by omega c. Right? These are the basic equations. Then what? Then what? Phasor diagram and power. Okay. So phasor diagram, if you see phasor diagram in all the three circuits, phasor diagram. So phasor diagram here, suppose if this is voltage V naught, okay, this is the horizontal line, let us say this is making omega t. So current here will go in the same, right? Current voltage waves both will be in same. So I and V are in phase, or you can say no phase difference, no phase difference, no phase difference between current and voltage. But when you draw here diagram, this is the voltage V naught omega t. It is here in this case current I naught will be lagging by 90 degree. This angle is 90 degree. Okay. So here current lags by 90 degree, or voltage leads by 90 degree. So phase difference is 90 degree here. Phase difference is equal to 90 degree. Okay. Next, in this case, if it is V naught omega t, and in this case current is leading, current comes like this. So here the angle is like this. So current leads by 90 degree, voltage lags by 90 degree. Here also phase difference is equal to 90 degree. Okay, these things we have done. Then next we will write the power formula. Power. So average power here is equal to V, average power is equal to Vrms Irms, okay, or V naught by 2 I naught by V naught by root 2 I naught by root 2, so that becomes V naught I naught by 2. Okay, that's what it is. Next, in this case, average power is going to be 0. Here also average power is going to be 0. So in average power over one cycle, we are doing calculation for one cycle. So whether you take a purely inductive circuit or purely capacitive circuit, average power over one full cycle is 0, right? But in purely resistive circuit, there is average power, okay? That is V naught I naught by 2. Clear? I think up to this much we have covered. Yes? Fine. So today now let us start LCR series circuit. Try to understand concept. Don't try to remember formulas. Formulas automatically will come. Even if you forget, it will come within seconds. If you remember the concept. Tomorrow is the DNET exam. Let's hope the questions will be difficult only because hopefully they are going to make it tough. Okay. So last time when the question happened, right? Then after just after the exam, I think that night or next night I was traveling. So some students sent me the paper. Then I made the means, video also. You can see on the channel. Full paper video is there. Okay, and whatever I had pointed in that paper, some of the questions were ambiguous. Whatever I pointed, the same issue was happening in that questions. Okay, and many people later also clarified the same thing. When question of significant figure was there, right, the NTA had given the wrong means according to NCRT they were giving, but that was a contradiction. Okay, similarly, one or two questions also was like ambiguous. Okay, it's okay, but you need to go through everything properly. That is why you need to understand things properly so that you don't have to mug up things. But at the same time, NCRT they are giving more preference for NEET. Any contradiction will happen, they will only consider NCRT answers or whatever point they were mentioning in NCRT, that only. So last time means this time the exam that happened, many things were directly from NCRT paragraph, and many teachers were criticizing that what is this means, why are they doing like, because last year it was question was good level, tough level. Okay, so this time also people were thinking like that, but they made paper very easy. But now in we need when it is happening, and tomorrow we'll see what happens. They will definitely keep tough only. Okay, let's hope. So that is why you prepare for the tougher side. NCRT you keep at the center, but prepare for the tougher levels. Okay, then let us move to the next. And if you have started preparing NCRT, start from the first chapter. Okay, I have already started NCRT series, but till now I have made NCRT videos only on the motion in a straight line. Complete videos I have made, detailed analysis I have done, and for example also I have made. Only the long answers I have not done. Okay, that I will also do. But if you look for the solutions for your board exam perspective, you may look. But the thing is that you need to understand more details, because NCRT is in depth, very, very deep it is. Every line has so many meanings that you have to properly understand. And what is NCRT says, that's one key meaning that you have to understand. There may be some side meanings also, but the key central meaning that you have to get, right? That we should not miss, because in assertion reasoning question they are asking that questions like based on the exact meaning of that. Okay, so you focus right now, you start NCRT, very, very important. Okay, let's start now. LCR series circuit. So series LCR circuit, series LCR circuit, series LCR circuit. So series LCR circuit means we have everything in series. LCR, inductor, capacitor, resistor, all of them are together connected with the AC source. Okay, and this is same as V naught sine omega t. Let's take this point as point A, this point as point B. So in between A and B, this AC source is connected. Now, what is important is to know, first of all, we should try to make a differential equation. The solution of that we don't have to do, because it will come a second order differential equation. And what is the goal of all this circuit analysis? The main goal is we want to find current. How current, what is the formula for current, and how much phase difference is there between current and voltage, right? Like in purely resistive circuit, there is no phase difference, zero phase difference. In capacitive or inductive circuit, phase difference is 90 degree. Okay, so same thing here, goal also is there. We want to find the equation of current, and we want to see what is the phase difference, and we want to calculate the phasor diagram we want to make, and also we want to find out average power. All these are the goals of the circuit analysis. Okay, right, so let us start this. So first let us apply KVL. So in this loop we are going to apply KVL. Apply KVL, Kirchhoff's voltage law. So when you go in the direction of current, so first let us make current. Let us say current is going like this. Okay, at any instant it is. So at that instant, let us say this is positive, this is negative. Current is going like this way. Okay, so in the inductor, let us write the voltage. So voltage across this in the direction of current minus L di by dt, right? Then voltage across the capacitor, you are going from higher to lower because this is going to develop plus q and this will develop minus q charge, because current is going here, so positive charge will develop here. So plus q minus q, so you are going from higher to lower voltage, so minus potential difference q by c. Again in the direction of current, minus IR. Then you are going from minus to plus, plus V is equal to 0. Sum of all potential drop is going to be 0. Now let us rearrange this. So you can say that L di by dt plus q by c plus I into R is equal to V. Okay, and we will substitute. We can substitute. Okay, but note that I want to get a equation in terms of current I want, right? Charge we need to remove because this term has current, this term also has current, but this term does not have current. So q you need to differentiate, that means you have to differentiate the entire term, and here v is equal to v naught sine omega t. So let us differentiating with respect to time, with respect to time, both sides differentiating with respect to time. So this side L comes out constant differentiation of di by dt. Di by dt differentiation will become double differentiation, right? Because you are going to differentiate di by dt. So di by dt differentiation with respect to time will become d square I by dt square. Then here 1 by c comes out. Q differentiation dq by dt. Dq by dt, you know, it is called current, right? Dq by dt is current, right? Plus here R is constant, R comes out, and this I differentiation means di by dt. Right side voltage V naught comes out, sign differentiation become cos omega t, and also the internal differentiation we are doing omega. So now let us rearrange this. So now we will rearrange. So divide everything with L. So you will get d square I by dt square plus 1 by LC into I plus R by C di by dt is equal to omega v naught by C cos omega t. Right? This equation we got. Let us first write double differentiation, then let us write single differentiation. So we'll bring the single differentiation second term. Okay. So do that. And what Sam? Oh, yeah. You please restart. You will get. Others, please note this. Okay, I'll continue then. I will repeat again afterwards. Okay. So d square I by dt square. Then second term I will bring first R by C di by dt. So did I divide by L or C? Sorry, I divided by L now. I made a mistake here. Okay. I have divided by L, right? So this term is L. Okay. So R by L di by dt plus I by LC. I just rearrange this. So first term I am taking this, second term and then third term. This is equal to omega v naught by L cos omega. So this equation which we have got, this equation is called second order differential equation. Second order ordinary differential equation ODE. Second order ordinary differential equation. Clear? Second order differential equation. Okay, Sam, now it is working. Okay, okay. Sometime we need to restart it, and also you can clear some cache memory. You know how to clear cache memory, right? In the laptop. You should know something about the laptop because sometimes laptop runs slow because of those things. These are like temporary memories. Like suppose you are using regularly, so the laptop will be opening so many files, right? And those they store as temporary memories, and that will be occupying some space. Sometimes it will go in GBs also. So we should delete those temporary memories, right? So because I all know all this because I worked in Infosys for almost 2 years as a project on system. Huh? Why did this discontinue? Means it was so much hectic. Means Infosys work was so much hectic. Means I was working and the shift was. Huh? But now this is my passion. That time that was not my passion. For job I went. So I did not like too much sitting in the computer and just coding and solving bugs issues. So many things were there, but I didn't like. And also many like the shift was there. You have to rotate in the shift. Rotate means they will not keep same shift. They will sometimes keep morning shift, evening shift, night shift, and so much health problems also there. So that is why I left. Otherwise, it was very good job. Means good, we get money and everything was fine only. But when I applied for PhD, then I went there. I thought it is some change has to happen in life. Okay, so I thought it is better. Anyway, I have good means technical knowledge about subject, so I will go for research. So I went for research. I give an interview, but I thought that they will not select me because already I am working, right. So people, those who don't have jobs now, they will go for PhD to do higher academics. Generally, it happens like that. But I had job and I went, and some questions I could not answer in the interview. My written was okay, but interview I could not answer anything because they were asking some practical knowledge. I didn't have any practical knowledge on research because after MTech only they go for PhD. But I was the BTech. After BTech, I just was applying for PhD. Right? So I could not answer many things in the interview panel. So many professors were asking some questions, but I could not answer. But I thought that I will not get selected. Then I thought that okay, I have to work there only. So I went and I was working, and one day suddenly means I got some letter, and I got that letter that you are selected for this PhD program. You go. Then I thought that okay, it is better now to leave that place and go there. So somehow it arranged, right? If you want something, if you keep on thinking that okay, I have to do something, it will happen somehow, right? Okay. So you also think about this, like I want to get good score, I have to work, I have to improve. In the brain, it will keep on going, right? And that thing influence, that has an influence, right? So definitely, whatever you keep on thinking, it will come into action. Sooner or later, it comes into action, right? Okay, so this is second order differential equation. After making this KVL Kirchhoff's law, you are getting this equation, but charge is, we have to differentiate charge. That's why entire term you have to differentiate. It will come in terms of current I, and then bring the differential equations in terms of double differentiation and rearrange that. So first term you write as double differentiation, next is single differentiation, and next term is only current, no differentiation, right? In this order you write, and then equal to this, right? So this is second order ordinary differential equation. Even in the J syllabus or NEET syllabus, the solution of this is not there. Okay, how to solve first order differential equation, that is there in the maths, but second order differential equation solving is not there in the maths. Okay, so that is why we do not go by solving this by usual method. We are going to solve using phasor diagram. Phasor diagram is a very important concept, okay, because phasor diagram definitely they, in NCERT lot of concept of phasor diagram is there. If you remember in oscillation chapter there is phasor diagram applications, right? In grade 11, okay, phasor diagram in oscillation. Lot of questions also NCERT has given in the exercise, and here also you are going to see the application of phasor diagram. Okay. So now let us start with this, how to solve this. So that means we want to find out current. What will be current? Okay, so how to solve this? Let us start this. So how to solve this? We start by assuming the solution. We start by assuming the solution. So we say that the solution will be like this. Solution will be I equal to I naught sine omega t plus phi. Okay, so we know already the voltage. Voltage is V naught sine omega t. We know this is the voltage. So we assume that the current, solution of current is like that. Why do we assume it like this? That is the first thing we have to ask. Why are we not assuming in terms of cos or anything else? So because we are dealing with phasor, right? We are dealing with phasors. So voltage is a phasor, so current will also come as a phasor. Why? Because we have seen in purely resistive circuit, purely inductive circuit, purely capacitive circuit, it is a phasor with some phase difference. In purely resistive, phase difference is 0. In purely inductive or capacitive, phase difference is 90 degree. Similarly here we are assuming it like this. So some peak value will be there, I naught and sine omega t plus phi. Phi will be the phase difference with the voltage. So we are assuming it like this. So let us draw the phasor now. So let us first draw the which phasor? Current phasor we are going to draw. Current phasor we will draw. So this is current phasor. Okay, current phasor we have drawn. And note that because this inductor, capacitor and resistor, all of them are in series, so same current is going to pass through it. The current which is passing is same, I, okay, same current, because they are in series, okay. But voltages will be different, right? What are the voltage? Let us say voltage across this will be VL, voltage across this will be VC, voltage across this will be VR. So voltage across resistor means inductor is VL, across capacitor VC, across resistor VR, right? these three voltage. But definitely we know that in series sum of all the voltage is equal to the applied voltage, right? So VL plus VC plus VR is equal to the applied voltage V. And this equation is happening at any instant of time. Anytime you see the voltage, sum of all the voltage equal to. And if you apply this equation for RMS also, then also it is correct. That means RMS voltage across inductor plus RMS voltage across capacitor plus RMS voltage across resistor is equal to the total RMS voltage, source RMS voltage. Okay. So whether you apply this equation for RMS or instantaneous or um, average or peak value, anything you apply, it will be same, that equation will be true. Okay, right? So that's the main thing. Now let us try to do that. Now what we are going to see is we are going to study now individual element. So this is inductor and this is the current. Remember, here current is same, but these voltages may be different. Voltages are different, but current is same. Because current is same, I am not going to change this diagram. I will keep this diagram same, right? And this angle already I have drawn. This angle is omega t plus phi. This already I have decided. Okay. So now you see this. Let us study inductor. So in an inductor, what happens? Current is lagging by 90 degree, right? Lagging, right? So now let us draw the voltage for that VL. So voltage VL must be leading, then voltage must be leading, and current is lagging, voltage must be leading. So this is VL. Okay. Same way, if I take about the capacitor, in capacitor current is leading, voltage is lagging. So voltage will be lagging for this. So voltage will be lagging by 90 degree. Let us say this is VC, and note that these angles have to be 90 degree, 90 degree both sides, because the current is the same. From the same current it is leading and lagging. Okay. And also note that now VR also I will draw. So VR, if you see VR and this current in a resistor, there is no phase difference between voltage and current. So VR I have to draw in this direction, in the direction of current. This is VR. Okay, done, right? Clear? All of you got clear idea about this? Yes. Okay. Now note that the sum of these are like vectors VL, VC, VR. Sum of these three vectors will give V, right? And if I am taking amplitude, generally when I am representing like this vector, this represent amplitude, right? This represent amplitude. So these are the amplitudes now. Now here it is amplitude. So let us add the amplitudes, right? Vectors we will add. So it will depend now which vector is larger, because they are opposite, right? VL and VC is opposite. So which is larger? We can take three important cases. Now we are going to take three important cases. First, case 1. Case 1. I will take VL larger than VC. VL larger than VC. VL larger than VC means I we are taking peak, everything is peak, so I naught XL must be greater than I naught XC. Yes, voltage is I naught into XL. I naught is same because they are in series. Current is same everywhere. This you can take instantaneous or this you can take peak. While drawing this phasor diagram, we always take the peak. Okay. So let us do that. Okay. So that means I naught get cancelled. XL is going to be larger than XC. And what is XL? XL is omega L is greater than 1 by omega C. Then omega square becomes 1 by LC. So omega becomes greater than 1 by root LC. Okay, this is the condition. So the frequency, assuming that frequency is greater than 1 by root LC, or VL is greater than VC, or XL is greater than XC, these conditions we are taking. Okay, These conditions we are going to take now. So what happen if VL is greater than VC? The resultant will come this side. Suppose this is 10 Newton and this is 2 Newton. You know, this side total will be 10 minus 2, 8 Newton. Same thing we are doing here. This vector is larger than this vector, so resultant will come this side. So let us redraw this diagram for this case. So we will find out this vector VL minus VC. Okay, and here we have taken a horizontal line, and this we have taken this as current I know, and this angle we have taken already, and this side we have taken VR, and this angle we have taken omega t plus phi. Right. Now VR and VL minus VC, they are at 90-degree angle, we know that. So let us now add them. You know how to add vectors. So the resultant of this will be coming in this direction. This resultant is what is V naught, because it is the vector sum of all the voltages. Vector sum, and this is what is V naught. Okay. But we know that from the horizontal line, this angle, this angle must be omega t, because voltage angle is always omega t. Correct? Voltage angle is omega t, and this is omega t plus phi. So definitely phi must be negative. Correct? Because this omega t plus phi is smaller than omega t, so phi must be negative. Correct? You have to subtract that. So suppose, let us now put phi as a magnitude. Suppose put the phi as magnitude. So I am going to keep this as omega t minus phi. Right? Why minus phi? Because we know that phase difference is going to be this way. Right? This angle, this angle, this angle is what is phi. Okay? Phi. So this is omega t minus phi. When you do, then this is the angle or the phase angle for the current. Are you clear about this? Yes. Okay. So the phase angle phi you need to subtract. Then only, that means you can say current is lagging than voltage. Current is lagging than voltage by some angle, not by 90-degree, because if it is 90-degree lagging means it will be purely inductive circuit. But it is not lagging by 90-degree, it is lagging by some angle. That angle may be any other angle, okay, but not 90-degree. Okay, right? So that is what it is. So here we can clearly see in this diagram that current I lags behind voltage by phi. Right? So phi is the phase difference. Phi is phase difference. Phase difference between current and voltage. Right? Again it is happening. I think you need to clear cache memory. You can try once. You press the window button and R. Window button will be there, na? It is window R simultaneously you press. The command window will open, right? Window R, when you simultaneously press, na, you will find open. Type the name of program, right? So there you type percentage, temp, yes, temp. Then again percentage you put percentage symbol. Okay. Hmm. No, symbol percentage symbol, percentage symbol, then temp, then percentage. Okay, then you enter. Okay, you do. What do you get? 1 minute. It will open temporary files. It will open a folder named temp. Is opening? No, no. See, I will tell what did you type. Did you type this? I'll put in the chat and just check. Okay. Did you type this? Check. Ah. So when you type this and OK, then there will be temporary memory folder will open. Ah. Yes. Then select all. Then do select all and just delete all these. These are all temporary files. And select all, delete everything. It will delete all these are temporary files which occupies the memory. Okay. Some of these may not get deleted if you try to delete because they may be system files. Yes. So whatever is deleting, you delete that. Then you have to check. You may have to restart and then you can check. It may become little bit better. Okay. So current lags behind voltage by 90 degrees. Fine. Anyway, I think I don't know much, but you need to check. Sometime some other issues might be also happening. Okay, so you need to check. My laptop also some issue happens, but some clear memory. If I do, most of the issues get over. Okay. Anyway, that you have to check. Okay, so here current and voltage means phase difference will be 5, right? We got this idea. Now here we want to find out what is this tan phi and all these calculations we can do. It is possible to do that. Let us do the calculation. So we know that the sum of this vector Vr and the sum of this vector Vl minus Vc, that sum is V naught, right? That sum is V naught, and these two are perpendicular vectors, so we can clearly say that this Vl minus Vc whole square plus Vr whole square, sum of this must give us V naught whole square, or V naught will be under root of this, correct? Because V naught is the hypotenuse and these two are perpendicular on base. So now let us try to simplify this. So VL we will write as I naught into XL minus this is I naught into XC whole square, then plus VR is I naught into R whole square is equal to V naught. So from here I naught I will take common and I will divide that side. So I will get this ratio V naught by I naught. Then this will be left with XL minus XC whole square plus R square. So this term is what is called impedance. Impedance of the circuit. This is called impedance. Impedance. So impedance is just like resistance of the entire AC circuit. Root under XL minus XC whole square plus R square. That is called impedance. Okay. Then we can also calculate tan phi from this. If I calculate tan phi, so tan phi is equal to this VL minus VC, VL minus VC by VR. Again, VL I will write as I into XL, I naught XL minus I naught XC divided by I naught R. I naught will get cancelled. It is like XL minus XC divided by R. Okay, so like this we can calculate the impedance, we can calculate this angle phi from here. Okay, then what else? Power how to calculate? So power also, current peak value also we can calculate because Z we have calculated, so current also we can calculate. How to calculate current? I naught is equal to V naught by Z. Z already we have calculated, root under XL minus XC whole square plus R square. So now we can say that we have got the amplitude of current and we have also got the angle phi from here. We can write tan inverse if you want. So phi can be written in terms of tan inverse XL minus XC by R. So we have now got everything. We have got the amplitude and we have got the phase difference. That was the purpose to solve. Now let us calculate average phasor diagram also we have seen. Okay. And here we can clearly say that it is lagging, right? So which is lagging? Current is lagging. Current is lagging. How much? By angle phi. So but it is not lagging by 90 degrees. So it is not purely inductive. So it is called predominantly inductive, predominantly inductive circuit, predominantly inductive. It's not fully inductive but predominantly inductive. Okay. Then power, let us calculate power. So power is equal to V into I. V is V naught sine omega t and I is I naught sine omega t plus phi. So now this can be written as V naught I naught. Let us bring sine together, sine omega t into sine omega t plus phi. Now according to trigonometry, we can transform sine c plus cos c minus cos d formula. What is cos c minus cos d formula? Is 2 sine, this formula is 2 sine c plus d by 2 sine d minus c by 2. This formula you have to remember. Okay. So if I consider sine c plus d and sine d minus c as a and b, so I can write this as 2 sine a and sine b. Suppose if I take a and b, if I take this as a and b, then what will be c? Tell me. C you will get by adding, no, by adding you will get d, right? By subtracting you will get c. So subtract. So this will be a minus b. Okay. Minus by adding you will get d. So this is cos a plus b. So you remember we are going to convert this sine a into sine b using this. Okay. So from here we can understand that sine a sine b can be written as cos a minus b minus cos a plus b whole divided by 2. This formula we are going to use it here. This is the trigonometric formula. Okay. So let us use this here in this. So V naught, I naught, sine we are going to use this. So it will become cos minus cos. So cos A minus B. A minus B means what? Remember A is the larger one here. Correct? Because I have taken C plus D. So here note that A is larger than B. If A is larger, I am going to take that. So this one is A here. Okay, this angle is A here. This angle is B here. So we need to do A minus B. So when you minus, you will get 5, right? And minus, when you add them, you will get cos 2 omega t plus 5 divided whole divided by 2. So this is the power formula we have got. This is instantaneous power. Now we have to calculate average power over one cycle. We are going to do the calculation for average power now. This type of proof they can ask. Okay. Let us do average power. Integration of power dt over one cycle 0 to t divided by total time t. Here power has this term V naught I naught by 2, you take out V naught I naught by 2, you take out. Then you have to integrate this cos phi minus cos 2 omega t plus phi. This whole term you have to integrate dt, and this time t I am putting it here. Okay, and integration limit is 0 to t. Let us do this integration. So V naught I naught by 2t Cos phi is a constant, so while you integrate, you will break this and this. So cos phi is a constant, so cos phi will come out. Integration of dt will give us t. Okay, cos phi into t. Then minus cos 2 omega t integration you have to do this whole term. Cos integration becomes sine. So you will get sine 2 omega t plus phi divided by the coefficient 2 omega. And now you put the limit 0 to t. Try to do this calculation. So V naught I naught by 2t. Put the upper limit cos phi into t minus put upper limit, so it will become sine 2 omega capital T plus phi divided by 2 omega. Upper limit is over, right? Minus lower limit. Time 0 will become 0 minus this will become sine phi. Sine phi it will become, but time 0 means 0 by 2 omega. Now let us open this bracket and also note that sine of 2 pi plus x is same as sine of 4 pi plus x is same as sine of 6 pi plus x. This you should know. Why? Because time period is t you are adding. Okay, this is same as sine x. So when you add the time period, it value will repeat. Suppose you add in this angle 2 pi, the same answer will be there. If you add extra 2 pi, 4 pi, 6 pi, same it will be as sin x. That you should note. Because sin value repeat after the period, right? So sin 0 is same as sin 2 pi, same as sin 4 pi, same as sin 6 pi. It will repeat. So same thing happens here. You know that omega t is 2 pi and 2 omega t becomes 4 pi. So here sine of 4 pi plus 5 will be same as sine 5. Okay. So this term which is sine 5, and when you open if you want you open once, okay, and you see that it is getting cancelled. So V naught I naught by 2t, this is cos phi into t minus that becomes sine of phi by 2 omega. Open this minus minus plus sine of phi by 2 omega. You see this term is getting cancelled now. This term got cancelled. So finally you got the average power. Average power you got V naught I naught. This TT also get cancelled when you open. So V naught I naught cos phi by 2. Now this can be written as V naught by root 2 I naught by root 2 cos phi. So finally we can say that average power can be written as Vrms Irms cos phi. This formula that we are getting is the formula which we have to use for series LCR circuit. This formula is only for series LCR circuit. And this factor cos phi is called power factor. Power factor. And this cos phi can be calculated from the phasor diagram. If you have seen the phasor diagram here, because we have calculated tan phi, right? In this triangle, we have calculated tan phi. Because this was VL minus VC and this was VR and this was V0. This was the angle phi. So here tan phi we have calculated. But suppose I want to calculate cos phi. So cos phi will be what? What will be cos phi? You can calculate cos phi. Cos phi will be VR by V0. Cos phi will be VR by V0. Okay, and what will be VR? VR will be I naught into R, and V naught will be I naught into Z impedance. This got cancelled. So you got R by Z. Z if you want, you put it. Z is root under XL minus XC whole square plus R square. Okay, so this is how cos phi can be calculated, right? So this is overall everything related to that LCR circuit series. Anyone in doubt, ask. This is all about results here. Now, but the thing is that you may ask, what about the case 2, case 3? Case 2 is simple. Just the VL, here VL was greater than VC. That case will be VC will be greater than VL. The diagram will little bit change. There you don't have to worry in that. Okay. So this is case 2 if you take case 2. Case 2 if you take. So what happens is that this VR was there here, right? So now we are going to consider this VC minus VR, because we will take VC is greater than VR. Okay, so then XC will be coming greater than XL, and here omega will come when you substitute 1 by omega C. So omega will come 1 by root under LC, less than that. Okay, these condition will come, and this was angle, and the current was in this direction, right? Current is in this direction, I know. Now here if you see, when you calculate the voltage, this VR and this, right? So this voltage when you calculate, it will come like this, V naught. So now you see that voltage is lagging or current is leading. So current is leading by 5. Same thing will come. Now you will see that this was omega t, and remember this current we have already taken, that this is omega t plus 5. Omega t plus 5. So here it is omega t plus 5. There it was omega t minus 5 because it was lagging. Here it is leading, right? Current is leading than the voltage. Okay, so everything will remain same. All formulas remain same. Nothing is changing, because why nothing will change? Because inside the root, if you put XL minus XC whole square or XC minus XL whole square, that's the same thing, right? So everything will be same, because a minus b whole square is same as b minus a whole square. So the formula for z is the same, root under xl minus xc whole square plus r square. For the sake of purpose, you may write it as xc minus xl, because you are saying that xc is larger, so you take it like that, but it doesn't matter. Okay, and current amplitude you will calculate same as V naught by Z. Impedance is the same impedance. Okay, and you will calculate phi same way. Tan phi you will calculate same way. Tan phi you will calculate XC minus XL by R. That's all. Power formula will also be same. Average power formula is also same. V naught or VRMS, VRMS, IRMS, cos phi. Right, power factor formula is also same. Everything is going to be same, but if you want, you write xl minus xc, instead of that xc minus xl you write, but it will not make difference because it is square inside that. Okay, that's what it is. So this type of circuit where this xc is greater than xl or omega is less than 1 by root lc, that is called predominantly capacitive. Capacitive. Okay, predominantly capacitive, and you can clearly see that here current is leading, right? Current is leading, so current leads by 5, or voltage lags by 5. Phi is the phase difference phase difference between current and voltage. Done? Yes. Did you understand this? Then the last case is very important case, because in that you have what? You have resonance. That third case is the most important case. Your questions are coming on the third case mostly. Okay, so let us go for third case. For case 3, case 3. Okay, so in the third case, they are going to cancel out. What are they can cancel? VL and VC are equal. So VL VC cancels out, right? If you draw the graph, this was VL and this was VC. This was VC, right? And this was VR, and current was also in this same direction. right? This was the current direction. This angle was 90. So this is the case where this length and this length are equal. So definitely they are going to cancel out. They cancels out. So this VR is the only resultant because they cancel out. So VR is only going to be equal to V naught. Okay, right? That's what will happen. And so the only thing here is that if I have to calculate Z, Z is root under XL minus XC whole square plus R square. But here XL and XC are going to be equal because they got cancelled, right? Because I naught XL is equal to I naught XC. I naught cancel, that means XL and XC are equal, right? This condition is very important. It's called resonance. Resonance. Okay, so Z is going to be same as R. So here phi is going to be 0. Note that because current and voltage is in the same. No phase difference between current and voltage. No phase difference. No phase difference between current and voltage. No phase difference between current and voltage. Okay, right. That's what happens here. This circuit is behaving like a purely resistive, right? Because in purely resistive, current and voltage phase difference is 0, right? That's what happens. It is behaving like it behaves like it behaves it behaves like purely resistive circuit. And also note that cos phi, the power factor is going to be 1. Power factor. Power factor cos phi is going to be 1 because phi is 0 here. Okay. So if I want to calculate current, okay, very interesting thing to note that when we write the formula for current, peak value is V naught by Z, and in general the Z formula is root under XL minus XC whole square plus R square. This is I naught formula, correct? But in this I naught formula, note that you may change XL and XC. But when this term is becoming 0, then this 0 is the minimum value of the denominator. Why? Because square, right? This is square. So the minimum value of square is 0. It cannot be negative. So square of XL minus XC, square of this minimum value will be 0. So because this is minimum, so at resonance, at resonance, I naught becomes maximum, and the maximum value of I naught is equal to V naught by R. Okay, this is going to be maximum. That means the peak current become maximum. Note that the peak current I naught is peak current, so peak current becomes maximum. Peak current becomes maximum. Okay, that is happening at resonance, and lot of questions are going to be on resonance, right? So now the next topic that is connected is the resonance, sharpness of resonance, quality factor of resonance. Those things are there. Okay, and the most important is the derivation of quality factor. Definitely the derivation of quality factor can come in your board exam. Okay, but I have derived a formula for quality factor which will fit in many different application, which is just not based just on NCRT, but it will overall it can take any type of questions on that. One very good formula, then maybe in your class they may give that formula, but the derivation of that formula is based on binomial theorem, binomial expansion we have to apply, and then we can prove it. Okay, so let us take that, we can finish that topic because resonance is finished once, then you can solve most of the questions, because after that eddy current and transformer, these are the only two topics which are not that much weightage. Few questions may come on that, right? But the most thing is resonance, sharpness of resonance, right? Most important and most high weightage topic in this. Okay, so let us consider that, cover that. Okay, so we can clearly see that the current formula of the peak is equal to V naught by root under XL minus XC whole square plus R square. This topic that we are going to discuss is the sharpness of resonance. Sharpness of resonance or quality factor. Quality factor. Okay, sharpness of resonance or quality factor. Now we know that at resonance, at resonance, at resonance, I naught is maximum. This is the maximum value, which comes as V naught by R. Why? Because we know that XL is equal to XC, right? XL is omega L and that is 1 by omega C. And you can solve omega also. Omega you bring this side, so omega square become 1 by LC. This omega you can calculate as root under LC, 1 by root LC. So this is called resonance frequency. Okay, this term, let us call this as omega naught. Okay, omega naught. So this term omega naught is called resonance frequency. Resonance frequency. Okay, resonance frequency. So when the frequency of the circuit of the AC supply becomes equal to omega naught resonance frequency, at that time current peak value become maximum. Peak value of the AC current, that peak value become maximum. Okay. Now, but suppose if I do not have a frequency which is same as this, the frequency of this AC source is not equal to this, it may be something else, right? Then resonance is not happening, then you have to use this formula to get the current. But when resonance happens, then this is the current, right? This is the current. But let us say if you try to plot this graph, suppose if I am going to plot a graph of peak current versus omega. Omega means the source frequency. Source frequency you are tuning, you are changing. And you will find that when this source frequency become equal to resonance frequency, at that time this value or this graph is going to be like maximum. Okay, this graph is going to be maximum. Note that this graph is not a symmetric graph. Many textbook, even including NCRT, they believe that it is a symmetric graph, but this graph is not a symmetric graph. When you are taking that this graph is symmetric means you are making some approximation. You are making approximation, but the graph is non-symmetric. Everywhere you see it looks like symmetric, but the graph is non-symmetric. Okay. Now here the most important calculations that you need to know here is that this peak value of this, right? This is I naught maximum. This is I naught maximum. Okay. This is what is I naught maximum. Now here, suppose if I choose a frequency very nearby to this, okay, note that I am going to choose a frequency very nearby to this. Let us call this frequency as omega 1, and similarly let us call this frequency as omega 2. Because I have chosen this value very close to this, then I can say that this is almost symmetric we are going to choose, and this difference is called delta omega. So omega 1 will be nothing but omega naught plus delta omega, and omega 2 will be nothing but omega naught minus delta omega. So delta omega more and delta omega less than resonance frequency. Okay, so these are two frequencies for which you will be getting the same value of current. Some I will be there, I naught, we do not know. Right, some I naught will be there. Now here you assume that this I naught is going to be uh, little bit smaller than that. How much is small? Definitely it is smaller, right? Because this is the maximum, this is little smaller. So let us call this as I naught max divided by n. Consider that this is smaller, but how much is smaller? It is smaller divided by an n factor reduce. It is reduce this by n factor. Okay. Now try to calculate this. Substitute here in this condition, and we want to calculate omega 1, omega 2, or we want to calculate delta omega. Note that this 2 delta omega is called bandwidth. 2 delta omega. So 2 delta omega is called bandwidth. Bandwidth. Bandwidth means it is the difference of omega 1 minus omega 2. That's what. Okay. This is called bandwidth. So we want to calculate this quality factor. So quality factor formula is what? Quality factor is defined as like this. Quality factor is defined as this bandwidth. Sorry, this resonance frequency by bandwidth. This is the definition of quality factor. Okay, and this is also known as sharpness of resonance or sharpness. Okay, so we have to derive. The derivation is important. Now let us write this main formula and consider derivation. So I am chosen I naught formula already we have written V naught by root under XL minus XC whole square, correct, plus R square. Now I naught I have chosen as I naught max by N. I have chosen some factor. So this is by V naught by root under XL minus XC whole square. XL minus XC, now I am going to substitute values. Okay. So we are going to substitute. Let us substitute XL as omega 1 that frequency, because you can either substitute omega 1 or omega 2, because the same value of current is at either of these two frequencies. Let us put omega 1 L minus 1 by omega 1 C whole square plus R square. Okay, and I naught max, now you substitute. I naught max value is what? I naught max value is V naught by R. Resonance, right, at resonance. And this will become V naught by root under omega 1 L minus 1 by omega C whole square plus R square. Now this V naught will get cancelled. And now you square this. Let us square this. So if I square this, it will become N square R square. Denominator, both sides denominator are equal, so square this. It will become omega 1 L minus 1 by omega 1 C whole square plus R square. This R square terms I will bring this side. So N square minus 1 times R square will take common, right? And then this will become omega 1 L minus 1 by omega 1 C whole square. Let us take under root over both. Let us take under root. So it will become root under N square minus 1. R square under root R will come out. And this become omega 1 L minus 1 by omega 1 C. Now let us solve right side. Right side we are going to solve. Solve right side. So this omega 1 I will write as omega naught plus delta omega. Right. Here omega 1 also I will write omega naught plus delta, or minus also you can write, it is your choice. Okay. Now I will take omega naught common from here. This L also I will write here. So 1 plus delta omega by omega naught minus, here also I will take omega naught common in denominator. So omega naught I take common, so 1 plus delta omega by omega naught. C also I can write it. But note here, I will write this C before itself. Okay. Here I will write C. This C I will write this side. So I will write this as omega naught C. Okay, because omega naught only I have taken common. Why are we writing it like this before? Because omega naught and 1 by omega C are equal. So we are going to take omega naught, because omega naught L is equal to 1 by omega naught C. We know this because this is resonance frequency. So this term and 1 by this term is equal. This term and this term. So either of this we can take out. So let us take omega naught L out. So what are we going to get here? You will get 1 plus delta omega by omega naught, right? And here it is in denominator. This denominator will take as reciprocal. So 1 plus delta omega by omega naught power minus 1. Now we will apply binomial approximation. So omega naught L is 1 plus delta omega by omega naught. Note that now equality will not hold. It is approximation now, because we are going to assume that omega naught by omega naught delta omega by this is much smaller than 1, or we are assuming that delta naught is much smaller. This is the approximation we are applying. Approximation. Assumption in approximation. So while we are doing this approximation, we are making this assumption, then only we can expand. So you know binomial expansion, 1 plus x power n becomes 1 plus mx. When do we do this? When x is much smaller than 1. That's what we apply the binomial approximation. So here we apply this, okay, minus, this is going to be 1 minus delta omega by omega naught. Right, now open the bracket both and check out. So you are getting this as omega naught L, open that, 1 plus delta omega by omega naught minus 1 plus delta omega by omega naught. So you are going to cancel 1. Let us just write equality now. Omega naught L, and this becomes 2 delta omega by omega naught. Correct? So from here, what do you get? You get omega naught, this get cancelled. You get 2 L delta omega. And what was left side? What was left hand side? Root under and square minus 1 times r it was. Correct? So from here you got what? You got 2 delta omega. See, 2 delta omega we are getting. 2 delta omega, which was bandwidth. We wanted to calculate bandwidth. Bandwidth we have calculated. So root under n square minus 1 times r divided by L. That is the bandwidth formula. Okay, bandwidth formula is. Now here you need to note that in NCERT, the value of this n has been taken as root 2. The value of n is taken as root 2. So according to NCERT, this formula will become root 2 square means 2 minus 1. So this term will become 1. So this will become r by L. Right? That is what is 2 delta omega. Clear? That's what it is. Yes. Did you find out the answer? Hmm. No, you didn't get in NCERT. Hmm. There is a reason behind it, because integration, if you do, you don't know the limits, right? If you do indefinite integration, you get the constant, but how do you get the value of that? 0. How to take that? Something is there, okay, that we will discuss. Okay, if you want, just think about it, because in LCR circuit, in LCR means that was in capacitive circuit, inductive circuit, right? In inductive circuit. So note that if you are giving the voltage signal with respect to time, that graph of voltage is like this. Correct? The graph of voltage is like this. And you are starting a inductive circuit. You are putting this V equal to P naught sin omega t. and this is the inductor. So we have got while we are doing that integration, we have got this I is equal to I naught um, minus of cos omega t. Means this is the final result we have got. Correct now? Right? Right? It's the final result we have got. So you think about, because while we are doing the integration of current, we do not know the initial value of current. Correct? Initial value of current. So while doing that, I think we have done this L di by dt, right, as equal to this V naught sine omega t. Correct? That's what we have done. So then we have written di L is equal to V naught sine omega t dt. Integration we have done. Correct? Right? So the limit of this current, but time limit is 0 to t, that we know. Correct? Na? Time limit we know 0 to t, initial time and other time. So right side when we are doing integration, definitely we can say, because sine integration comes as minus cos. Correct? Na? Sine integration comes as minus cos, right? Right hand side. Sine integration comes as minus cos omega t by omega. Suppose if I put the right side limit, we get this, right, and put upper limit minus cos omega t minus minus plus 1 comes, right? Correct? That one comes. But here what is the limit? Final value will be I only, but initial value we do not know. Correct? Initial value you do not know. Now think about it. Here it looks like some maximum value is coming. If you try to see here the graph, this is the voltage graph, right? This is the voltage graph. So suppose you have just switched on, this is plus minus, just when you switch on, what do you think will be the current here? Will current be 0 or current be maximum? That is what it is. So the integration limit current will not be 0, current will be the maximum, and that maximum current is, that is what is V naught by omega L. This L you can take this side, okay? When you take this side, it will come here. This L you can put it. Omega, right? So the idea is that the maximum current, that means initially itself current is maximum. Try to understand this. Initially itself current is maximum in that circuit. As soon as you connect with the AC source, initially itself current is maximum. We should not take initial current 0. Initially we should take current as maximum. That is the main reason we have to do that. But why do we take initial current as maximum? Why do we take initial current as maximum? Why? Because if you see here the slope of this graph, the voltage is changing here, right? And here the voltage that we get is rate of change of current. Rate of change of current, right? V voltage across the inductor is L di by dt, correct? Di by dt means rate of change of current, and rate of change of current and rate of change of voltage will be related. Suppose here if you see the voltage is not changing, right, at the peak value, because slope becomes 0. This is dV by dt becomes 0, correct? But initially the slope is maximum. This is what you need to note. Initially the slope dV by dt is maximum. You should know that in a sine graph, slope is maximum here or here. Here it is minimum because negative slope. So slope is maximum here. That means voltage is very quickly changing. And because of such quick change of voltage, the current is maximum initially itself. Because inductor property is like that. Inductor will be, because inductor behaves like induction, right? Induction happens. So if something changes in that inductor, then only induction happens. Correct. If inside the inductor coil, if change is not happening, right, then the induction will not happen, right? So here at this instant, change is maximum. That's why initially the current itself is maximum. So when you are taking this limit, you have to take this as maximum current here. Okay, you have to consider maximum current. Maximum current you have to take, then you can solve. Otherwise, if you have solved without any limit, suppose you have solved without any limit and we have got C, right? We have got C. We have got like I think this we have got. Correct, na? Like this we have got. Some constant we have got. Correct? This type of constant we have got. So when you are going to see here current, so current will be initially what? Initial current will not be 0. Correct? Initial current will not be 0 because when you put time equal to 0, let us say, when you put time equal to 0, I becomes equal to minus I naught, this become 1 and that becomes C. Now see, when can this constant be 0? When this current, this initial current is going, this I naught is not initial, I naught is peak value, okay. This initial current I am taking, let us write this as I initial. This is I initial. So this I initial will be minus I naught. So that this and this get cancelled. That's why that C comes as 0. Are you understanding this? Yes, Sam, are you getting? Because C will be 0 only when this I initial should be equal to minus I naught, right? Why it should be minus I naught? Because see here initially the slope of this voltage is maximum. Slope of voltage is maximum, and in the coil what happens according to Lenz's law, the coil will try to oppose, right, coil will try to oppose. So as soon as voltage change is maximum, the current will be the minimum current. So that current, but magnitude of current is maximum, but the current I initial you have to write minus I naught. Okay, minus is showing the opposite direction. That's why this minus I naught and this minus I naught they get cancelled, because current maximum is I naught, right? Peak value of current is I naught. So here that's how C comes as 0. Okay, are you getting? This is nowhere explained in either in NCRT nor in any textbooks. This you have to understand by this only. That means sometime if they give you the question that what happens at time 0, current is minus I naught. Current is value is maximum, but it is opposite minus because it is opposing the voltage. Voltage is increasing, so current is going to decrease to its minimum value. Okay, that is the reason. Understood? Got this? So now this topic is over, sharpness of resonance. But in resonance, now that formula you remember. Huh? Here in NCRT they are using this value. Okay, R by L is 2 delta omega. This is also the quality factor, and then they do some calculation of quality factor will be this. This is a bandwidth. Sorry, quality factor is this, right? Quality factor formula is omega naught by 2 delta omega. So when you substitute this 2 delta omega, this is R by L. So this is what it is. Okay. This is quality factor or sharpness. Okay. And what is meant by more sharpness or less sharpness means if the graph is like this and the graph is like this. So if you consider this as the omega naught value, here also omega naught value. And if I consider the width very large, so here you see the width is very large, right? This is 2 delta omega. But if I consider small width, then this is the small width, 2 delta omega. Okay, so small width, whenever the width is very small, this is called more selective or more sharpness, more sharpness. Okay, here this is more bandwidth, this is called less selective, less selective. Okay, less selective or less sharpness. Got it na? Done. Okay, so now you just go through this. I think most of the things are over. Now the current and the transformer, that topic is there that you can cover up. Now you solve questions. If any doubts are there, you send me. Okay, then we will discuss that. Fine. Okay, bye all. Bye. Yeah, thank you. Good night. Good night.